Hi, in this video we'll be looking at introduction to mobile robotics. So we'll be understanding the concept of mobile robotics in the basic form. So mobile robots are robots that move from one point to the other. Now the method by which they move, that is the method of their locomotion, can be either wheeled or legged, which means a mobile robot that has a leg like an insect or like a human being and moves from one point to the other. However, the other type, which is the wheeled type, that means you have a robot that has wheels. And that is the medium by which it moves from one point to the other. Now, of these two kind of locomotion, the wheeled is the most applied. Why is this? Is because the mechanism for wheeled locomotion is simpler compared to that of the legged locomotion. So based on that, you would see more of wheeled propelled mobile robots as compared with the legged kind of locomotion in mobile robots. And the types of wheels that you can have, there are basically 4 types of wheels for the wheeled mobile robot. You have the standard wheel. The standard wheel just looks like that you have in vehicles. So these are wheels that only rotate about a fixed point. It's just like you have in vehicles that rotate about a fixed point. The castor wheel are the wheels that rotate about the fixed point, also about their contact point, and also about the castor axle. If you kind of picture the your office chair, you have this kind of wheels that spins around under your office chairs that makes you change your direction even while moving the chair around. So it rotates about the center of its own axis, also about the contact point, which is the ground, and also about the castor axis. However, for the standard wheel, it only rotates about the contact point and about its own center. So this one has 2 degrees of freedom, while this one has 3 degrees of freedom. Also, you have the Swedish wheel. Swedish wheel also is kind of similar in terms of degree of freedom to that of the castor wheel. So these are wheels that has rollers on their circumference. They have a lot of rollers on their circumference. So the rollers can be inclined in 45 degrees, just like this, or 90 degrees, just like this other one. So the rotation is about the rollers, the contact point, and the motorized axle. So about the center point where the motor is spinning, then the rollers also are spinning, and also about the contact point, which is the ground in this case. And also you have the ball wheel or the spherical wheel. So these are wheels that they are referred to as omnidirectional, so they can go in any direction at any time. So let me just go to Google to show you some of this. So this is just a mobile robot with a standard wheel in this case. So this is just a standard wheel. So you can have a castor wheel. So let's go and check. So this is what a castor wheel looks like. Also, this is a castor wheel in this case. So rotation about the points, the motorized axis, rotation about this very castor axis here, and also about the ground, which is the contact point. Just like you have a rotation about this point, rotation about this castor axis, and the ground contact point. So this is your Swedish 45 or your Magnum wheel in this case. So this is Swedish 45. You can have Swedish 90 also for mobile robots. So this is your ball wheel in this case. Let me just zoom. So this is your ball wheel. Let me close this. So this is also another ball wheel. This is still your Magnum wheel or your Swedish 45 wheel. in this case. So this is the motorized ball wheel in this case. This is the ball wheel here. This is omnidirectional kind of wheel. Also, this one is your Magnum wheel, or your Swedish 45 is equally omnidirectional. So the rollers are spinning. There's also rotation about the motorized axle and also about the ground contact points here. So this is the ball wheel. This is the caster kind of wheel. However, for a mobile robot to properly discharge its duties in a certain environment, three things are very important. Number one is the navigation and the localization. So under navigation, we have two things, which is the path planning and the path tracking. So what is path planning? Path planning is the method by which the mobile robot knows how to move from one point to the other, and there are several algorithms by which this is done. You have the A-star algorithm, you have the your Q-learning also is an algorithm that is being used for path planning in mobile robotics. You have a lot of other algorithms for path planning in mobile robots. So what your path planning algorithm would do is to plan the path. In most cases, you want the shortest path from one point to the other in that environment. And also, the path tracking is the form of control that you are using to ensure that, because at the end of the day, it's your DC motor that will do the work. It's your DC motor that will move the wheels of the mobile robots around. So the path tracking is a control that you are using to ensure that your mobile robots stay close enough to the planned path as possible. So you want to ensure that the mobile robots stay as close as possible to the planned path as possible. So that is the control you're using. That's the path tracking in this case. Then localization is the method by which the mobile robot itself knows where it is in the environment relative to where it is going in that same environment. So that can be probably through a GPS or something, whereby the mobile robot can know where it is relative to where it's going, or probably you can use a barcode. So as the mobile robot moves in the environment, it scans a barcode, and that barcode gives it an information as to where it is in that environment. So from there, the mobile robot can measure where it is coming from to where it is and relative to where it is going. So just simply put, you have something like this, mobile robots work in a 2D environment, because when you're talking about mobile robots, they are basically 2D. So you have an environment like this in 2D, whereby this is your y-axis and this is your x-axis. So probably you have obstacles in the environment, because for you to do a path planning, every path planning algorithm you want to use would ask for the map of the environment, the 2D map of that environment, if it's a mobile robot in this case. So you can use any method to do that in probably in Windows or in Linux, depending on the system you're using. So you can use any method to create that environment and put it into your path planning algorithm. So let's assume that this is the goal point. This is where the robot is going. This is the destination in this case. This is where the robot is going, and this is where the robot is starting from. So this is the mobile robot itself. So it has two wheels, one on the right and one on the left. So this is the robot itself, and this is where it is starting from. Now this very point where the robot is corresponds to a certain coordinate on X, because if you measure this on X-axis, and also a certain distance on Y, in this case on Y. So this is where the robot is. This point will be probably, let's say, X 20 units on X-axis, and probably on Y-axis, maybe let's say 2 units on Y-axis here. And this destination also corresponds to a certain coordinate on X and on Y-axis as well. Just something like this. So let's say for the destination, let's say it's Y100. Is Y100, while x for the destination is, let's say, x5, so the algorithm will ask you, okay, where is the robot, what is the coordinates, and what is the coordinate of the destination itself. So what the algorithm will do is to plan a path, and also the algorithm will ask you where are the obstacles, because there can be two kinds of obstacles in an environment. Is that they are dynamic or they are stationary? So when you have stationary obstacles, it will ask you where are the stationary obstacles. However, when the robot is moving, the robot will take care of the dynamic ones, because dynamic ones will be sensed by the robot, and depending on the method you are using to evade dynamic obstacles, maybe it's a weight procedure whereby if there's a dynamic obstacle in your path, wait for it to pass. Whatever way by you are using to sense obstacle, maybe you are using ultrasonic or infrared or an RL sensor or whatever on it. So you have a destination here, you have the robot here, the coordinates. So what the algorithm would do is to find a path, to plan a path. Let me say it now plans this path in this way. Now, okay, this is the path, this is the best path. Don't go through here, don't go through an obstacle, go through this point. So all the coordinates on this path will be listed by the path planning algorithm. It will list all the coordinates of all these points. It will list them out. So what the path tracking wants to do is to ensure that the robot, the center of the robot at all time coincides with every coordinate that has been listed by the path planning algorithm. So the control that you are now using to ensure that the center of the robot, depending on the movement of the robot wheels from the DC motor, makes the robot to stay on track, to ensure that the center of the robot coincides with the coordinates. So that is the path tracking. Now the localization in this case is, how would the robot know that I've moved from this point to this point and from here to here? So that is localization. So how would the robot know where it is in the environment relative to where it is going in that same environment? So that's just an idea of localization, path planning, and path tracking for mobile robots. Also, there's another important aspect of mobile robots, which is the kinematics. And we know that kinematics is the study of motion of a body without considering the responsible forces. So you have a mobile robot that we know that it is the DC motor or whatever actuator you are using that propels it. However, I want to study the motion of that mobile robot without considering the actuators that is causing that motion to take place. So that's the kinematics in this case. And the example of the wheel configurations that we'll be using is the differential drive wheel mobile robot. So why do we say it's differential drive? We're saying that you have a mobile robot whereby the wheels on the right and the wheels on the left, their rotation, or let me say the wheels on the right and the wheels on the left, they are powered by different DC motors. Each wheel on that robot is powered by different DC motors, so it's not as though a single DC motor is controlling all the wheels, but every wheel has its own DC motor attached to it. So that is what is called a differential drive wheeled mobile robot. So just like the image that we have here, you have the VR, that is the velocity of the wheel on the right, and also the VL, the velocity of the wheel on the left. So you have the wheel on the left, wheel on the right, having their independent DC motors. So it becomes a differential drive DC motor. So A here is the center of the robot itself. L here is the distance between the two wheels, and C is the center of the two wheels. So you have the global coordinates in this case. We already said that mobile robots operate in 2D space. So that's your YG and your XG in this case. However, we said that in mobile robotics, what the path tracking wants to do is to ensure that the center of the robot, which happens to be the center of the actuating wheels now, coincide with the coordinates which is being printed by the path planning algorithm. So here is the center of the two wheels, which is point C. So that's where you have this Y and this X in this case. And you have the robot coordinate on itself from the center of the wheel, which is the YR and XR. So if you measure how the XG, which if you transmit it will still be here, has rotated to XR, so that is your theta in this case. So that is how all of this came about. So the global reference frame is your XG, C, and YG, while the robot local reference frame is the XR, C, and YR, which is what you have here. This is for the robots, this is for the global reference frame in this case. So C is the center of the two wheels, L is the distance between the wheels. So the position PG, which is the position in this case, that is this column vector X, Y, and phi, which is the orientation, X and Y is the position. So if you transpose this from this column vector, you will get this row vector. So it's just a transpose of that. And also if you differentiate position with respect to time, you get your velocity in this case. So if you differentiate your X in respect to time, your Y in respect to time, and your phi in respect to time, you will get your velocity, which is the first derivative of your distance in X, Y, and your angle here in this case. So for a differential drive wheel mobile robot, when the velocity of the left wheel is equal to the velocity of the right wheel, then that robot is moving on a straight line for differential drive. However, when the velocity of the wheel on the left is greater than that on the right, so the robot will turn in the direction of the wheel with the lesser velocity. So what that means is, for a differential drive to turn it to the right, the velocity of the right wheel will be less than that of the left, so that the robot can pivot around the right wheel, which is having the lower velocity. And to turn it to the left, the velocity of the wheel on the left will be lower than that of the right, so that the robot can pivot itself around the left wheel, which is having the lesser velocity. So for you to cause a differential drive mobile robot to spin on the same spot, all you need to do is to ensure that the velocity of the right and left are equal. However, one is positive, the other is negative. So with that, the mobile robots, the differential drive mobile robot will begin to spin on the same spot, which is what I'm just trying to state here. So if we do the resolution of forces of what we have here, so if we resolve into X and Y, so the velocity of X will equal R divided by 2, which is the radius of the wheel, VR plus VL into cos phi. Also Y, velocity in Y-axis, equals R over 2 VR plus VL sine phi. And your phi itself is R divided by L into VR minus VL. So this is the kinematic model for a differential drive mobile robot in this case, just by resolving this into X and Y components and taking the first derivative of it to have velocity, just like what we have here. So but for us to actually solve this properly, so we'll consider a unicycle. A unicycle is a mobile robot that has only one wheel. For instance, you might have seen a bicycle has two wheels, then a unicycle will have just one wheel. So if we have just one wheel, that means VR and VL will just be a single V. in this case. So we just have one V here, and a single V here. So that is why we have, so this is the kinematic model for a unicycle, whereby you have only one wheel, and the velocity of that wheel is the velocity of that very robot in this case. However, for a differential drive, the velocity of the robot is the average of the velocity of the right and the left wheel. So that's why you have r over 2 in this case for the velocity in x and in y axis, because for a differential drive, the wheel on the right and on the left are driven by different DC motors. So to get the velocity of the robot itself, you have to take the average velocities of the two actuating wheels. So, but for a unicycle, it has only one wheel. The velocity of that wheel is the velocity of the robot itself. So that's what you have here. So for the velocity of the robot for a differential drive mobile robot, that will be the radius of the wheels divided by 2 into velocity of the wheel on the right and that of the left, and the orientation of the robot itself will now be r divided by l into VR minus VL, just like what you have here. So your V robot is the robot velocity itself, while VL and VR are the velocity of the right and left wheel, and the angular velocity is your omega robot, which is this in this case. So we can substitute equation 3.9, which would be this very equation in this case, VR. So if you make VR the subject here and you make VL the subject in this case, you get this expression for VR and VL just by making VR and VL the subject in this very equation. You get this out. You can try that and you get that out. So the next thing you want to do is just to make the equations uniform. So like we already said, the relationship between the mobile robot velocity and that of the two actuating wheels, as given by these researchers in 2015 and in 2017. Like we already said, for a differential drive mobile robot, the velocity of the robot itself is the average of the velocity of the wheel on the right and that of the left. So that's just what they are trying to represent here. And also the orientation in this case is the difference between the two velocities of the right and left wheel divided by the distance between the wheels. That's just what they are trying to explain. However, for each of the wheels on a mobile robot, either as your VR or VL, is the radius of that wheel multiplied by the omega of that very wheel. Now this omega is your 2 pi n over 60. Same for your right or your left. The velocity of a wheel by itself is the radius of that wheel, then 2 pi n over 60, which is this omega in this case. So if we replace this into the equation given by these two researchers, so replace VR VL with R omega R and R omega L. That's what we have here. So this is VR, this is VL, this is VR, this is VL. So if we simplify this further, we have R over L, omega R minus omega L, which is what we have here. And if you also simplify this, you have R over 2 into omega R and omega L in this case. So that is just the model for the velocity of a differential drive mobile robot as explained here. Okay, so I want to explain the concept of dead reckoning. How do you use a wheel encoder? Because we know that encoders are used to measure revolution. So if you have a wheel and you have an encoder attached to it, which is an optical sensor in this case. How do you use an encoder to actually build an odometer to calculate the distance covered by your mobile robot? So for encoder sensors, we already know they are optical sensors, and we know that they have what we call ticks per revolution. So every encoder has ticks per revolution depending on the manufacturer of that very encoder. But how do we use an encoder to build an odometer? That's where the concept of dead reckoning comes in. So for every manufacturer, they will tell you number of ticks per revolution of their, so they'll tell you the number of ticks per revolution. And then just erase this. So they'll tell you the number of ticks. So they'll tell you ticks per revolution of their encoder. So it depends on the manufacturer in this case, number of ticks per revolution of that very encoder. So for the encoder that is now attached to a wheel, let's say this is a straight line and you have a wheel here. This wheel has its own diameter, and let's say this is where the encoder ticks from. So every revolution comes back here for one revolution. So how many times would the encoder tick before this one revolution of the wheel has been achieved? So that will depend on the manufacturers. We have DC motors that are already configured with encoders, so that when you're buying the DC motor, you can buy the one that has encoders already, so that it makes your work very simple. So if this wheel should move this distance, maybe cover this distance, so we want to know, how do we use the encoder ticks to know the distance covered by this very wheel? So that's just what we want to explain. So the number of wheel revolution now, so number of wheel revolution in this case will now equals to, so will now equal to the number of encoder ticks. So that will be total encoder ticks in this case. So that will be total encoder ticks. That will be total encoder ticks divided by total encoder ticks divided by the tick of that very encoder per revolution, which will be given by the encoder manufacturer in this case. So that will be given by the encoder manufacturer. However, if this wheel should rotate one revolution on this plane, the center of this wheel would have traveled a distance that equals the circumference of this very wheel. So one revolution of wheel, so one wheel revolution in this case will equal to the circumference of a cycle, which is 2 pi r. The circumference of a cycle as 2 pi r. This r is the radius of the wheel in this case. So the distance traveled by this wheel now, so that will be the distance traveled by this wheel. So the distance traveled by the wheel, just a single wheel, will equal to the number of revolution of the wheel, number of wheel revolution. So that will be number of wheel revolution multiplied by the circumference, which is 2. Sorry, let me erase this, which is 2 pi r in this case for this single wheel. So number of revolution, we know it is this. So we can just replace this, substitute that into this equation. So distance traveled by the wheel will now be the total encoder ticks. Now the total encoder ticks. So that's total ender ticks. Total encoder ticks divided by ticks per revolution, which will be given by the manufacturer in this case, multiplied by the 2 pi r in this case. Multiplied by the 2 pi r. And we know that the radius of the wheel is constant. The tick per revolution is constant. So the only thing that will be changing is the total encoder ticks. So that's how you build odometer using an encoder. So for instance, if this is a differential drive mobile robot, to now know the distance that the robot itself will cover will now be the average of the distance covered by the two wheels in this case. So this is just for one wheel. So if you have a differential drive, so that will be the distance covered by the right wheel plus the distance covered by the left wheel divided by 2 will be the distance covered by the robot center itself. However, the only input that will be changing is the encoder ticks for the right wheel and the encoder ticks for the left wheel, because we know that the ticks per revolution of the encoder is constant and the radius and the pi is equally constant. So the only variable here is the encoder ticks. However, this method for calculating the distance covered by the robot might not be very effective. It's not even might not, it's not effective, because if the wheel of the robot is sleeping, it's not covering any distance, it's just sleeping on the same spot, the encoder will keep ticking, thinking that the robot is moving, whereas it is on the same spot. The wheel is just gliding on that same spot, So that is why the science of localization is very, very important. Even if the encoder has ticked a million times, the robot can still be on the same spot. However, if you use a very established localization method, we said localization is a method by which the robot knows where it is in the environment relative to where it is going. So a GPS or a barcode will always tell the robot that, okay, your encoder might have ticked this number of time, but your coordinate is still the same due to what the GPS is saying or due to the barcode you scanned in the environment. But on the lower level, this is how you can use an encoder to build an odometer to calculate the distance a wheel has covered, which is being called the dead reckoning in this case. So in this video, we have been able to look at the introduction to mobile robots, also the mobile robot kinematics for a differential drive mobile robots, and also the principle of dead reckoning. So thank you very much for your time, and we'll see you in the next video.